Okay, so in the last lecture, we saw how the reaction rate, the rate expression, is a function of concentration. And we alluded to the fact that the rate is actually a function of concentration and temperature. In this lecture, we'll see the temperature dependence. So in the last lecture, we wrote the rate expression as equal to a rate constant, K, times a function of concentration. So this is where we get the concentration dependence. In this lecture, we'll talk about the rate constant, which is where the temperature dependence comes from. So the rate constant follows an Arrhenius equation. So K of t is equal to A of t times an exponential term. A of t is called the pre-exponential term, or sometimes it's called the frequency factor. And E is the activation energy. So together, these quantities determine or help to determine the rate at which a chemical reaction happens. So specifically, this A of t term, the frequency factor, this gives us a measure of the number of opportunities for a chemical reaction to happen. So specifically, it's the frequency of occurrences that could lead to a chemical reaction. So for example, if I have a gas phase reaction, then one of the things that needs to happen for a gas phase reaction to happen is that gas molecules have to collide with each other. So in that case, A of t could quantify the frequency of occurrences where two gas molecules collide. And so by frequency there, I mean the number of times per unit time that two gas molecules collide. So the A of t is the frequency factor. It quantifies the frequency of occurrences that could lead So it's telling us how often do circumstances align where a chemical reaction could happen. It doesn't tell us the number or the frequency of occurrences where a chemical reaction actually does happen. It's just saying how many times per unit time do circumstances lend themselves to a chemical reaction happening. So this term is the exponential term. Specifically, it's the exponential of the negative activation energy divided by RT. This term scales the frequency factor by the probability that a chemical reaction actually will happen. So this term is the probability that an occurrence, for example, a collision, does indeed result in a chemical reaction. So the probability So the A of t term gives the number of times that a reaction could happen, and then the exponential term gives the actual probability that the reaction does happen. Specifically, this term is a Boltzmann probability, which is derived from statistical mechanics. So an example to illustrate this is a gas phase reaction. So in the gas phase, reactions happen when molecules collide. However, molecules collide all the time. That doesn't mean they react. So think about the air that we're sitting in, comprised mainly of molecular oxygen, molecular nitrogen, and noble gases. Those molecules are colliding. That doesn't mean that they are reacting. For example, the nitrogen and the oxygen are colliding, but they're not reacting at room temperature. For those molecules to react to form nitric oxide, for example, we'd have to raise the temperature by a significant amount. And that's because those collisions are simply not energetic enough to hop the activation barrier. So in the gas phase reaction, the A of t term is quantifying the total frequency of collisions, the number of collisions per unit time. So it's even accounting for those collisions that do not have sufficient energy to surpass the activation energy. The exponential term scales AFT by that fraction of collisions that have sufficient energy to pass the activation energy. So at room temperature, if we think about the nitrogen and oxygen and air, the speeds of those molecules are not fast enough that the collision, when they do collide, they have the collisions are not very energetic. Now, if we were to turn the temperature up, those molecules would be zooming around much faster. They'd have much more energetic collisions, and some of those collisions would start to have sufficient energy to surpass the activation barrier needed for molecular nitrogen and molecular oxygen to react. So that's what this term does. It basically says there's an energy, there's an activation energy, and a collision, in this case, must have energy to overcome it. And that the ability to overcome it is going to be determined by the temperature. So if we draw that out, so this is a box, and in the box we have gas molecules, and all those molecules are zooming around. I try to draw that somewhat randomly. They zoom around really fast. The hotter the temperature, the faster they zoom around. Sometimes they collide. The frequency of which they collide, that can be predicted using theorems from physical chemistry. That's what gives rise to this frequency factor. And the speeds of the molecules when they collide, that determines the energy of the collision. If that energy is sufficient to hop the activation barrier, a reaction can happen. The probability that that energy is large enough to hop the activation barrier is determined by both the activation barrier itself and also the temperature. So in this equation, in this Arrhenius equation, E is the activation energy. You'll see this written in many ways. In this book, in this class, it's written as just E. It might be written as delta E of activation, or E with the superscript act, or something like that. What that basically means is the activation energy. What that is equal to is the difference in enthalpy between the transition state and the reactants. So when I say transition state, that is a compound with a chemical structure that's in between that of the reactants and the products. So for example, a reaction that makes a good illustrative example is the hydrogen cyanide isomerization reaction. So hydrogen cyanide reacts to form hydrogen isocyanide. So if we draw out these molecules, so the reactant is going to be this HCN, and the product is CNH. And the transition state looks something like this. So I have my C, I have my N, and this hydrogen here, what needs to happen is it needs to transfer from being bonded to this carbon to being bonded to this nitrogen. And it's not just going to appear and reappear, or disappear and then reappear. This structure has to contort itself somehow so that the bond, the breaking of the HC bond and the forming of the NH bond is possible. So what do you suppose that structure looks like? How should I draw this remaining, this hydrogen onto this structure? What should I do? Where should I put it? So I'm going to put it about right here. And it remains bonded to this carbon. The bond becomes elongated. And this nitrogen atom, it starts to be able to see this hydrogen up here. So it starts to think, oh, I could form a bond with that hydrogen. And that's what happens along this reaction pathway. The hydrogen, basically, the nitrogen-carbon-hydrogen angle goes from being about linear to being very nonlinear. And in doing that, the hydrogen approaches the nitrogen. If the energy of this complex, or if the temperature of the environment where this complex is is hot enough such that this molecule can surpass the activation barrier of this complex, then this reaction will happen. So notice how this species is contorted compared to the reactants and products. This contortion costs energy, so this is higher in energy, so it's less favorable than the reactants or products, and that's because this bond, this angle, in fact, this complex would much rather be linear. However, the way that this ends up contorting is when you turn the temperature hot enough, so all molecules, they have translational degrees of freedom, which is why they zip around. They also have rotational degrees of freedom, so if you were to zoom in on a molecule zipping around, it'd also be tumbling around. But they also have vibrational degrees of freedom. So all of these bonds are vibrating, for example, so the hydrogen and the carbon are vibrating against each other, the carbon and the nitrogen are vibrating against each other, but also the carbon is vibrating up and down. And at some point it will vibrate enough up or down such that the molecule will start to look like it's bent like this. So the hotter you turn the temperature, the more vigorously this thing will vibrate. So turn up the temperature hot enough and you may find yourself in this contorted geometry. But because this contorted geometry perturbs the molecule out of this linear state that it likes to be in, so you're contorting that bond, you're stretching this bond, you're making the geometry of this thing less favorable than it wants to be, and that costs energy. So that energy cost is what gives rise to activation energy. So we can illustrate all of this on what we call a potential energy surface or a potential energy diagram. So if I draw a diagram and I say energy, and this will be arbitrary units. And down here I have what I call a reaction coordinate. So in this case, it might be the linearity of the angle. I can draw the energy. So here would be my reactants. Here's my transition state. And here are my products. And then I can label on this diagram the energies that are important to us. So the difference between the transition state and the reactants, this is the activation energy. And then this quantity, if I take the difference between the products and the reactants, what is that? That's going to be my heat of reaction or enthalpy of reaction, my reaction energy. So this reaction coordinate down here, this tells us basically the progress of the reaction from a geometric perspective. Oops. So if we go back to our isomerization example, the progress might be this angle from being if you're looking at the NCH angle, for example, what went from being 180 is now to 0. So I go from about 180 to maybe 60 down to 0. So if you're interested in transition states, there's a lot of extra information on Canvas that I encourage you to pursue. There's an exercise there where you can actually calculate the transition state for this reaction using quantum chemical software. And don't worry, you don't have to do the calculations yourself. You use a graphical user interface and you submit it to the internet and you get an answer back. So there's a lot of good stuff there if that sort of thing interests you. Key point here is that the rate expression depends on concentration and temperature. The temperature dependence comes from the rate constant. There's both of the terms in the rate constant are dependent on temperature. One of those is the exponential term, which is the exponential of the activation energy divided by RT. This term increases exponentially with T. So this is because activation energy is almost always greater than or equal to 0. So as the temperature increases, this term gets larger and larger. The frequency factor, A of t, is often linear with t. Sometimes it's proportional to t to some small power, for example, t to the 1/2 or t squared. In this class, we're going to assume that it's constant with t. So in this class, we're going to assume that the temperature dependence of the rate constant comes from this exponential term. And usually, usually if we're in a regime where activation energy matters, that's the case. And usually we're trying to run in a reaction where everything has been optimized. We're trying to run in the situation where this term dominates with respect to temperature and this term is constant with temperature. However, there's plenty of scenarios where that's not true. But for the purpose of this class, this is a fine approximation to make.